Well, welcome everyone. My name is Laura Chappell. I'll be the moderator for this session, and I'm very excited for this session. Today we have Alberto Montilla. He is the founder, co-founder, and CEO of SPATIAM Corporation. You can get information about his company at spatiam.com. SPATIAM offers a DTN networking platform for use in space. They also do research projects for NASA and other space agencies such as JPL. I do recommend that you go out to the spatiam.com website and you take a look at the blog entries. They're fascinating over there at SPATIAM. Alberto has entitled his presentation today as Space Communications and Networking 101. This is based on course content that was developed for computer science students at Utica University in New York. It was developed further for presentation at the University of Texas in El Paso and other international institutions. So sit back and enjoy this course on space communications and networking 101. And now I'm going to hand it over to you, Alberto. Take it away.
Thanks, Laura, for the kind introduction. And as usual, let me go and share my slides. That's going to be part of the content. And good day, everyone attending remotely. As Laura indicated, this is a 101 course, Space Communications and the Interplanetary Internet. It goes into the technical foundations of space communications and then the needs for networking at interplanetary distances. And we're going to establish some concepts down the road. I'm going to skip this slide. I think we had enough of an introduction. And quickly on the agenda, we're going to start with space communications, the basics of how spacecraft communicate with other elements such as ground stations, and what is specific about communications in space. Then we're going to move to networking and the steps towards the interplanetary internet. And we're going to end up with some quick conclusions about why we're doing this, why we're building the interplanetary internet, and the move or the expansion of space just as a subject of exploration to space as an economy. So with that, let me start with the first chapter, Space Communications 101. And I'm going to start with an extreme example of space communications. And that, as many of you know, I'm going to talk about, I would say, probably my favorite spacecraft. And I'm sure it's the favorite of many of you is Voyager 1, being the first human-made object that reached interstellar space. Basically, the first human-made object that basically left the solar system. Think of it that it was launched 47 years ago, and it reached interstellar space more than a decade ago, actually in 2012, and it's still alive. There is a good documentary in Netflix that talks about Voyager, and also there is a good video that was recently released by the JPL Voyager team that talks about the recent work on Voyager. But now, coming back to communications, I just wanted to let you know some of the very extreme measures that constitute, the Voyager operations. The first one is the distance from Earth. It is more than 15 billion miles away. That's basically 166 astronomical units, and it moves pretty fast, 30,000 miles per hour, and I think it's 38,000, but let's say 30. I think it's 38,000 miles per hour. And then one very important thing is basically we have to wait close to 2 days to see if we're able to communicate with Voyager. That means that the round trip time, which is the time it takes for us humans to send a signal to a spacecraft and receive it back, it's 46 hours. So the one-way light time is 23 hours. It's a very long time. Put this in construct with how immediate are communications on Earth. When we look at the specific in communications, this communicates on the microwave X band right now, 8 gigahertz. But one of the things I want to highlight here is the signal level or the power received on Earth. Voyager has a 23 watts transmitter, and actually I have to admit I had to look at the literature, but basically we received a billionth of a billionth of a watt, and that's termed an attowatt. So very, very, very faint signal, but thanks to the Deep Space Network, we're able to decode the signal, demodulate the signal, decode the signal, and obtain information. How much we get, give or take, in normal operations is around 160 bits per second. But every bit that we receive, it's literally new information for humankind. That's how important this data is. For those that are as fascinated as I am with Voyager, you can follow it through on the JPL website, voyager.jpl.nasa.gov. There is plenty of information there, and there is a lot of literature, technical literature about Voyager and the communication system available. But think of it as, okay, wow, this is it's extremely far away. It takes a long time to establish a communication with or to receive data from the spacecraft, and it takes big antennas. So let's double click on that and establish some of the concept of why, how this is possible. And we're going to look at that in a couple of aspects. The first one is looking at the effects of distance in space communications or in communications in general. And on the left hand of the slide, you'll see the distance, and you see kind of three levels. What happens with space communications where or when we are somehow close to Earth, and these are the Earth orbits, and what happens with communications within the solar system, and then what happens with communications when we are outside of the solar system. And then you will see the effects that has in terms of what is the delayed experience and what happens with any signal that is transmitted across such distances. So when we look at the Earth orbit, and it started with the International Space Station, this is in the low Earth orbit, which is one of the closest orbits to Earth. Now we talk about very low Earth orbit, but let's stay to LEO. Low Earth orbit, we're talking about ISS is at 250 miles away. And in that case, the delay experience in communications, which is basically how long it takes for the signal, which travels at the speed of light, from ground to the station or from the station to ground. And in this case, it takes in the tens to hundreds of milliseconds. Then when we move further orbits, like the geostationary orbit, which is 36,000 kilometers or 22 miles away, then 22,000, miles away, then we're talking about several hundreds of milliseconds. So the delay continues to increase. But in that case, what happens is that the longer distance, the more signal or energy or power is lost as an effect of the distance. In a general formula, the signal loss is linear to the frequency and the square of the distance. So the more the distance, the signal is going to be affected by the square of it. So what we see is that the longer the distance is, we're going to lose more energy, more signal. Now, because we're talking about the interplanetary internet, let's focus around the solar system. And the first, planetary body satellite is the moon, which is, around 240,000 miles. And in this case, the signal delays are not only are no longer milliseconds, but are on seconds. So one-way light time to the moon is around 1.3 seconds. But if you take a second example, which is Mars, which is the next planet, we're talking about millions of miles, depending on depending where we are in this 2-year cycle between Earth and Mars. The distance goes from 35 to 250 million miles. So we're not talking about hundreds of thousands anymore. We're talking about millions or tens of millions or hundreds of millions of miles. And what happens in this case is that now we're talking about one-way communication delays for one-way communication delay of minutes, several minutes. And then if we start looking at the outer planets, we talk about delays of hours. And then longer distances, as we said before, bigger signal loss. And let's close with interstellar space, where Voyager is today, and thinking about the next star. And now we talk about trillion miles. So this tells us that the space volume is huge. But now the delays, we talk about days to years, depending on where, how close or how far that spacecraft would be in the future. So there are two realities here. The first reality is that real-time communications, or what we as humans understand as real-time communications, is no longer possible. Because, for example, if you are in communications with the moon, whatever information you receive happened at least, let's say, 2 seconds ago. If you are on Mars, if you're receiving communications from Mars, whatever information you received already happened 6 minutes, 20 minutes ago. And if you talk about outer planet, or you talk about interstellar space, things happened probably days ago. The second part of it is what we have to do to receive that communication, to demodulate that communication. So basically extract information out of it. And the longer the distance means more dollars, larger investments. Why? Because you need bigger antennas. We're talking about microwave bands. Parabolic antennas are the highest gains. You need a larger and a larger and a larger and a larger dish, which means level of investments that are very, very high. Just to give you an idea, the largest antenna that we have till now for radio communications in the DSN is around 70 meters. That's the size of a football stadium, and I don't know how many tons of weight. It's but not only it's the fact of real estate or how big the antennas are, but also the electronics. We start talking about electronics that requires close to zero noise or very, very low noise, and because of the law of thermodynamics, that means that you need to put those electronics at very, very low temperature, which talk about cryogenics electronics, and that also has a cost implication to it. So it's as conclusion, the effect of distance is twofold. On the one hand is communications. There is a inherent delay of communication just because of the speed of light. And the second is that there is a huge signal loss that you have to compensate basically with money to have better transmitter, better receivers, larger antennas. So that's the first major effect is distance, the volume of the space. The second major effect or cause in this case is disruptions. And that's caused by celestial mechanics. In space, everything is moving. Galaxies are moving, and within the galaxies, solar systems are moving. Planets are rotating. They are moving or translating between each other. There are effects like conjunctions where planetary bodies may not be visible because there might be something else in the middle, another planetary body, which is, for example, when you think about the Mars solar conjunction. And the effect that everything is that all these celestial mechanics create is disruptions in the communications. There is no line of sight because at the end of the day, radio waves in general communicate via line of sight. So each point has to see each other. In the case everything is moving or rotating, that inherently create a disruption and then loss of signal, loss of communications. And that's a great example when we think about communicating to the moon, to Mars, for that matter. So let's see how we compensate or how we handle those two main effects: delay and disruption. So the first one is, let's talk about one of the solutions, which is the use of relays, right? And basically, a relay is used to connect two moving elements. For example, a ground station on Earth with a spacecraft, in this case, let's say the International Space Station, which is in LEO, that is moving. So how you connect those two all the time? Well, you need a relay that has visibility to the International Space Station all the time and to a ground station all the time. Because just because of the orbit in which the International Space Station is, that there won't be permanent line of sight between the ISS to ground. But that same concept applied to any planetary surface. So for example, when we're talking about Mars or even the moon as a satellite, how you can ensure that a surface point on the moon can communicate with a surface point on Earth 24/7 is primarily by using relay satellites. And one example is what I have here on the screen, which is NASA TDRES. It's probably the most famous relay satellite constellation and that we have now that allows connecting elements in the different Earth orbits to the ground. TDRES is in the geostationary orbit and has been operating for quite some time. So remember, relay satellite allows to basically connect two moving parts, two moving elements. Then the second part is, how do we minimize those disruptions on Earth ground, because Earth is also rotating, and there is a very geometrical solution to that, which is basically placing ground stations spread out around the world. And there are nuances in terms of what hemisphere, whether it is in the north or south, but using the most basic form, if you think about if you take one plane, what you do is distribute antennas, so you ensure that in a space you have 360 coverage. At minimum, you need 3 antennas to cover, or 3 stations to cover 120 degrees each, which basically is the case of the deep space network, where there is a complex in California, another in Australia, another in Spain. Sorry. And then from Earth and where you play, or any planetary body, but let's use Earth because is where we have developed the satellite orbits. It's basically you find different places to place the satellites to have coverage of Earth, but also coverage of the other orbits. And we have the classical orbits, whether it is LEO, which is the medium Earth orbit, or the geostationary orbit, and then some specific ones which are the highly elliptical and polar orbits, etc., etc. And this is, again, making it super practical here. This is the ice.nasa.gov. I love this view. You can go at any point of time and see the deep space network, and the different complex, and how the different antennas are communicating to the spacecraft. So in this example, we are looking at the DSS 35 in Canberra in Australia, and that is communicating with the Mars Odyssey. And just look at this. The round trip light time is 26.5 minutes. So it's a very, very delayed communication. So how do we build this? So let me start with, again, in the how to build networks 101, we start with the physical layer. Physical layer means the radio link or the optical link. In this case, let's talk about radio. But the formulas are very similar, pretty much the same for any wave, type of wave. And the way this works is pretty straightforward. Depending on the type of signal, that means depending on the type of encoding we're using, depending on the type of modulation, there is a minimum level of signal that has to be received by the receiver so that it is able to demodulate and extract information from it. And this is a very standard formula that says that the power that is received by the receiver equals to the power that is transmitted by the gain of the antennas, multiplied by the gain of the antennas, and then divided by all the losses, which is the space loss that is based on distance and frequency, as we said before, the losses that happens in the transmitter and other miscellaneous, and the receiver and other miscellaneous losses. And these losses has to do with cable losses, because there is a cable from the antenna to the electronics, and other type of losses. So this is where it starts. Is basically establishing the physical links, and the way you plan for that is doing a link budget. And the link budget is nothing else that putting numbers to characterizing the link to ensure, and designing the link to ensure that there is always under very long range of conditions, there is always enough signal received so that information can be transferred. Information can be demodulated, can be. So if you go to this scanso.jpl.nasa.gov, you're gonna see a great all the the communication link designed for many of the interplanetary missions that has been launched by NASA over the years, and it goes to a very, very low level of detail, or very level of detail. So I encourage it for anyone who is interested in double clicking about how physical links are designed. Go there, you will find a lot of information. So think of it that we have a link established, and think of it that establishing a link allows you to communicate between 2 points. So now we see what happens next. So you have a link, there is signal, flowing through, but think of it that the main purpose of this is to transfer information. And you would say, okay, what type of information? Information that is typically is telemetry, and telemetry is the concept of data that is coming from the spacecraft. And typically these data include science data. And remember that the majority of them, if not the vast majority of the missions are related to understanding our place in the universe, understanding science. So there is a lot of science data coming back from sensors. There is also other type of data like imaging and data that is related to the operations of the spacecraft. Then a commanding goes the other way around, which is what are the control functions that the human operators act on the spacecraft. So if you want the spacecraft to, let's say, move or to activate or deactivate a specific sensor, these are control functions that are sent from ground to the spacecraft, and this is commanding data. And then you have data that is specific to tracking and navigation. Sometimes this data is just the signal itself. Sometimes it's bits and bytes that goes into basically the data flow. And last but not least, and this is a specific use, if you have a relay satellite, in this specific case, the purpose of the relay satellite is to relay data. Is basically the main use of the satellite is for communications. So in that specific case, the data may not be of use of the satellite, but might be of use of the ends where the satellite is connected to. In the case, it's a relay satellite. And depending on the type of data, you may imagine that the volumes may change, because if you think about telemetry, we might be downloading a 4K video. And in that case, there is the volume of data is pretty high. Or you may be downloading engineering or operational data that needs, the highest reliability. So that talks about the different levels that the data may be. It's could be high volume, high throughput, or it could be low volume but extremely high importance. And at the end of the day, this points to the fact that there are different classes or type of data when within a link. So with that in mind, CCSDS, which is the Consultative Committee for Space Data Systems, it's an organization that is formed by the space agencies, became a standardization body to basically enable digital communications with and through spacecrafts. And through that, there have been a series of protocols that were specified and are in use in space to basically create a data layer. Starting with, we already established the physical layer. So what happens then? The next step is, let's establish a link layer, which is how two endpoints can transfer data between each other. And for that, you need protocols that specify the framing, that specifies, for example, multiplexing, that specifies security so that the communication between 2 points is secure. And that's what I refer to as the CCSDS legacy space protocol stack. This is basically the protocol stack that was created and have been created to enable spacecraft to ground and then a spacecraft to surface communications. And there are some popular modern protocols that, those that work on space data communications talk about, like, pretty much on a daily basis, like CFDP on the application layer to transfer files, or SPP to frame or format packets, to Proximity One, which is a proximity link protocol specific to space, or specific to the last, what we call the last mile. So now we get to this concept, which is, okay, what we have talked about enables, the establishment of a physical layer, and enables the establishment of a link to allow two endpoints to transfer data, digital data between them. Where we are right now is that there is, and this is already happening in LEO, and it's going to happen on the moon, and it's going to happen on Mars, is that the number of assets with communication needs is increasing dramatically. To the point that, when we talk about the moon and then Mars, there are going to be astronauts, there are going to be habitats, rovers, energy systems, and a very large number of support elements. And they will need to communicate between each other, with Earth, with different users on Earth for operation science, etc., etc. When, similar to what happened with the terrestrial internet, then managing this type of networks requires the concept of networking. And what is the big difference? The big difference is that with links, you can connect two nodes to a physical layer. With networks, you can automatically connect any node and any application that are connected to the network. And the interesting thing is that because each node has an address or a series of addresses, you don't need to know, as an end user, very similar to the internet, you don't need to know what is the path that the communication is taking. You don't need to worry about that. And that's the beauty of the network, or networking, which is it allows you to connect elements to the network, and then pretty much automatically, of course, security aside, you can get any endpoint to communicate with another endpoint. Let me give you an example. On Earth, just to illustrate it, on Earth, you start up your computer, a new computer, you go to, your retail of choice, buy your computer, you turn it on, you get connectivity to your Wi-Fi, let's say, and immediately you can type google.com and you get connected to Google. you don't know where Google is, and probably you don't care. All you know is google.com, and Google don't know, at least initially, where you are at. But you connect between each other. So that's the power of networking that allows, moving from 5, 10 nodes to 100,000, 10,000, million, and billions of devices. And then what is going to happen in space is not different. So what I'm pointing at is networking is needed for a space in general. And the topic we covered today is interplanetary space. And why? I'm going to get there into a second. Interplanetary communications. So this goes back to 1998, where TCP/IP was already well established. There were service providers now providing internet services of multiple types. The first email applications, and basically a few folks, experts, starting with Vint Cerf and many from JPL, Scott Borley, Keith Scott, and many others, got together in light of understanding how to provide automated, networking with Mars, because of the fact that there would be a relay satellite in place. And they analyzed how the TCP/IP, the existing terrestrial internet architecture, would fit into it. And basically, the discovery and the conclusion was that the traditional terrestrial internet architecture had many architectural and performance issues that made it not suitable for its use at interplanetary distances. And some of those includes the fact that on Earth, because Earth is relatively small if you consider the volume of the space, internet is relied on infrastructure that is centralized on Earth, like DNS. Also, the protocols in general were very chatty and very connection establishment related, in which those protocols would stop performing in the presence of delay and or disruption. And in this case, 1998, the main use case analyzed was Mars. And all of that would rely on an architecture that would not guarantee a reliable transfer of data. And the solution to that was basically named as delay and disruption tolerant networking. Very easy, right? We already saw that the two main effects that space has in communications is delay and disruption. So let's build an architecture that is tolerant to these effects so that we can have a network with reliable transfer of data across any endpoint at interplanetary distances. So what is DTN, or delay and disruption tolerant networking? Some people, term it as delay tolerant networking. Basically, it's delay and disruption tolerant and networking, and it's basically a digital communications networking technology that its main purpose, as any networking technology, is to enable the reliable transfer of data across network elements. In this case, DTN network elements, when the propagation delay, the signal delay, is highly variable and or very high. In this case, the data transmission, because it is a network, it's performed automatically, even when one or more network links are not available during long time intervals. What that means is that the architecture takes care of the delays and takes care of, or is tolerant to, the disruptions. And even in presence of these two, the architecture can guarantee the reliable transfer of data between 2 points. And the main internet working protocol, think of it as, when we talk about TCP/IP, we talk about a TCP/IP stack, and it's there are a bunch of protocols. Here is not that different. DTN is an architecture, so it has a set of protocol stacks. However, in the same way as IP is the main internet working protocol for TCP/IP networks, in the case of DTN, the main internet working protocol is called the bundle protocol, BP. And bundle protocol is now an RFC on the Internet Engineering Task Force, IETF. This is RFC 99171, available for anyone to access and read on the IPF website. The bundle protocol runs as an overlay network over multiple network or link technologies. So it's extremely flexible. For example, the bundle protocol in ground, as you see here in mission control, for example, can run over TCP/IP. Why? Because TCP/IP is fantastic, when we are on Earth. But it also can run over space, over link technologies and space protocols that are dedicated or specifically designed for the space scenario. So, for example, you see here that in deep space, the bundle protocol may run over the glider transmission protocol, which is LTP. And there are other, other designs and other convergence layers, as it is termed. The second part of it is that networking, in general, is support scheduling, which are basically planned contacts. Saying, one of the good things about the space is that we can pretty much predict with very high level of accuracy when a specific point on Mars is going to be on line of sight with a specific point on Earth. So we can design with very good accuracy the schedules of communication. So the networking side, networking supports schedule contacts, or also opportunistic contacts. This is in case of the system can also work with signals that says that the links are up. And one of the things that is also very particular to the bundle protocol, with respect of traditional TCP/IP technologies, is that the networking layer itself performs store and forward. Why? Because as you know, and as we have been talking about, there may not be a link between one node and the next node for a while. So what do you do with the data that is incoming? You have to store it so that it doesn't get lost, right? So the networking performs store and forward. Every node has the capability to store data. And this is, I don't know if it's going to play well, but this is basically it's not going to play well, sorry. This is disabled, but there is a good, I'm going to look at the link and send it later, but there is a good animation that compares TCP/IP, UDP/IP, and DTN in presence of disruption, and how DTN is able to support a reliable transfer of data at any, DTN hop. So this is a basic performance example. I took this from the literature. These initial estimations were done, a decade ago, actually, that compares, the TCP/IP performance. And in the first one, you may have a look at Earth vicinity with round trip times in the milliseconds. So basically, that goes from 0 to 1 second. And you see the blue line is TCP/IP. And you see that the good put, the ability of the network to send information, goes, close to, 0, just at 1 second delays, right? And versus using bundle protocol, you see that the performance, depending on the bundle size, is much better. But when we look at the second graphic, you see here that the good put, and this is talking about round trip times of seconds, so much longer distances, where we see that TCP/IP, which is again the blue line, drops dramatically, just right there before 2 seconds. And then for the bundle protocol with LTP, where that's probably the optimal, you see that there is a drop, but then it's maintained. So it's like a 10x performance improvement. So this is just the basics of comparing TCP/IP just in the presence of delay. We're not talking even about disruptions here. So where are we? There have been great progress since 1998, where the first idea of the architecture was put together. There have been great progress on DTN and the establishment of the interplanetary internet. And just put some experimental highlights. I won't go into a lot of detail, but those the experiments got to a point went from initial experiments like the successful DTN experiments performed by NASA with the approximation in deep space. That basically was an 81-second delay, successful experiment, to basically controlling applications like the experiment of controlling a robotic arm through DTN performed by ESA on the ISS, to basically the setup of the first ever operational network in space with on the International Space Station, and that network is already still up and running on the ISS. It's basically managed by run and managed by NASA, to the point where other organizations, came in, started with the IPNSIG. The IPNSIG established the pilot project working group, established the first civil open DTN ground network, which is still in operations, and many of you can join if you decide to do so. It's our first attempt to have an open DTN network. Then in 2021, the DTN as a commercial company performed experiments on the ESA OPSAT satellite on LEO, performing interoperability tests between macro DTN and ION, and performing with the help even of IPNSIG members, performing a cloud vision application through a ring road, basically a data mule using DTN. And then in this year, many highlights. The PACE mission, which is an environmental satellite, is the first ever NASA Class B mission that used DTN operationally in a satellite. That's up and running. At the SPATIAM, we performed the technology demonstration in that International Space Station this summer very successfully, demonstrating a commercial DTN platform for space. And very, very recently, Scott Johnson and Spacely Packets perform a prototypical implementation of email service over Bonder protocol. So where this is going, basically this is going to full operations at a scale. And the big target is LunaNet. LunaNet is the Lunar Communications, Position, Navigation, and Timing Network Architecture Network Framework for the Moon, which is sponsored by NASA, the European Space Agency, and the Japanese Aerospace Exploration Agency, JAXA, with support of other organizations and the commercial industry at large. DTN is the main internet working protocol for lunar networking and lunar communications. And even beyond that, LunaNet is establishing the concept of LunaNet service providers, which is very equivalent to the internet service providers on Earth, but it's basically providing communications and or PNT, position, navigation, and timing services. And there is a whole architecture to how to connect users to the network and how to connect network to network to ensure the main purpose is to ensure interoperability so that end users can have reliable transfer of data through the network. So that's going to be a major formal steps towards, or the first phase of the interplanetary internet, fully operational as we know it. So that's fully in motion, both from the Moonlight project on ESA, also from the NASA perspective, and in collaboration with many commercial organizations and other institutions as well. So last, let me conclude with some of the reasoning, some of the why. So let me do a quick recap. We talked about the basics of space communications and the effects that delay and disruption have on communications because of the long distances, because of the frequent disruptions. How we can mitigate those effects, first at the link and physical layer by the use of relay satellites, by the use of antennas systems spread around the planetary body, and then by the use of better electronics, bigger antennas to ensure that enough signal is received, Then we look at, now that the physical layer is established, look at data communications and some of the protocols that are being used, mostly specified by CCSDS, and how we move into networking, which will allow us to scale data communications across the solar system in an automated fashion, and the role that DTN plays on it as a core internet working architecture for the Tolerant network. And we also saw that the first, implementation at scale of an open network is basically targeted to become, LunaNet a few years from now. What is this? What is LunaNet and the interplanetary internet enabling? Well, let's talk about the following, right? We typically say that space is hard to humans because there may be oxygen, there is gravity, there are some foreign components. We need our own spacecraft, which is a spacesuit to isolate from the environment. So one thing that we already know for a fact is that automation and robotics is going to continue to be a major element in space exploration and on the space economy. And we know, because of the parallels to Earth, that those autonomous systems, those robots, are going to generate a lot of data, in addition to the needs of the humans that are going to be settled or traveling to those locations. So similar to, if you think about that, there is no big difference with Earth. The space economy is going to be based on data, period. There's going to be a lot of data being transferred back and forth, a lot of data generated, a lot of data consumed, so that we're going to need the needs of networking and data transfer are going to continue increasing and enabling the space economy. I won't go into details, but this is just a very small highlight of all of the things that are being worked out. Some of them are very short term, some of them are a little longer term, but all the things that are, all the infrastructure that is being, an industry for that matter, that are being created or evolved in support of the in-space economy. And each of these elements, similar to Earth, are going to require a reliable and scalable network. In addition to that, and with this I'm going to close, this goes very, very much to the core of who we are as humankind. We have the need, the urge to communicate and collaborate. And the internet and the digital economy on Earth is an example. The space is going to need, even more reliable, even more scalable network, so that we can continue evolving now, outside or beyond Earth. So with that being said, if you want to know more, one suggestion, please go to the IPNSIG website. There is tons of general and technical documentation. There are the IPNSIG Academy webinars available on the IPNSIG, and also available, most of them available on the Internet Society website. For those that have a more technical aspiration, you can go, or interest, you can go and join the pilot project working group. You can join our network. There is a network of experts there to help you learn more about DTN, and all of this is offered, for free. And the whole reason is we do believe in an open network. We do believe in basically internet for all, which is one of the mottos of the Internet Society as well. With that being said, I just wanted to say thank you, and now back to you, Laura.
Well, that was incredible. Thank you so much for that. That was an amazing presentation, Alberto, and I have some questions here for you. This question comes up a bit when we do these presentations. What will the encryption standards be for the space internet? And we have a similar question. I think these two sort of go together, where we have Alan asking, saying that he's new to this topic in IPNSIG, but he's worked in cybersecurity for a while. Is there information in the IPNSIG library on the security features of DTN? And I can talk a little bit to the Zotero side of things, but in general, people want to know about security of space comms.
Awesome, Laura. And this is, specifically to interplanetary communications, and this is an evolving topic. So when you think about encryption standards, think of it that those encryptions in general, and I'm not talking about military use or anything about that. Let's just narrowing to the world of the civil operations. Encryptions per se may not be that different than what we have on Earth in terms of standards. There is a big nuance though, and this is more an architectural nuance, which is, for example, today public key infrastructures is based on a not only chatty but an infrastructure that is Earth based. So one of the things that are being prototype and architected for space is how you do delay and disruption tolerant key distribution. How do you move from the concept of potentially or expand the concept of public key infrastructure to something that is more related to the trusted collective? This is to handle the specifics of the very long delays and the disruptions. But when it comes to encryption itself, the security paradigm is pretty similar. It's basically how do you ensure confidentiality and integrity of the data at any point of time.
All right. And Vin put a note into before I go on, I just wanted to mention to everyone, there is a free Zotero library available to you online at IPNSIG.org. And if you're interested in the introductory topics, we have a folder there with just the introductory topics for you to move forward in your training. But Vin put a note in here into the Q&A area that I think is really interesting, and perhaps you can explain this a little further out to people and the idea of contact graphing. But it's important to remember that higher delays mean that antennas will have to be aimed to where the receiver will be in the future when the signal arrives at the speed of light. You need to lead the receiver by sending to a location ahead of the receiver's trajectory. Do you want to talk about that a little bit?
Oh, sure. I wanted to leave that to the 201.
Oh, okay. Well,
but yeah, I think this is a great concept to not only to imagine but to materialize, which is things are moving and they move pretty fast. So as Vint was saying, part of the routing, the specific routing protocols and to drive convergence in space has to analyze that, which is things are moving and you need to point the entire system starting from the physical layer to where things are going to be, so that the signal, considering the delay, the signal gets at the right time when the antenna is pointing, or the antenna is in the right place and pointing to the right place. Otherwise the contact or the communication opportunity won't happen. So that's also part of the plan of the contacts, how acquisition of signal is performed as well.
all right. And a question came in asking for how someone would gain experience with DTN related protocols, just as if you're experimenting, with a lab in your own system on IPv4 and IPv6 protocols. And if not, would you recommend someone to become more familiar with DTN concepts beyond reading the research papers?
Great. So the good news is that many of the vast majority of the implementations that are available today for the bundle protocol and for the bundle protocol stacks are open source. Starting with the NASA ones, you take ION, HDTN, you take BPLib on CFS, and DTNE, and these are just 4 from NASA, but also micro DTN, for DTN, all of them are open source. You can go to GitHub, download them, and start playing with it. They have great, fantastic documentation. Having said that, on the IPNSIG library, there are great links to training, very practical and hands-on training that would complement, that would help you on this day one. And then on day 2, my suggestion is to join the IPNSIG PWG, because it cannot be more real than that. There is a live network. You can connect your node. Now, once you know how to spin up a node and the basics of the node IDs and things like that, you can go to the PWG to connect and to basically talk to others, to continue learning and evolve.
And again, if you're not a member of IPNSIG, it's free. We are the Interplanetary chapter of ISOC also. So please join. Coming up in 2025, we have a very exciting project that is underway. I'm not sure whether I should even announce it or anything like that, but it will give you some hands-on experience, basically, in building your own interplanetary network node. Okay, there's a question that came in from Luis. Is there any possible use of a space-based cloud infrastructure? Challenges?
Yes. I mean, I would say it depends, but in general, yes. Thanks to organizations such as the ISS National Lab, NASA, they do have solicitations that are specific, either open or primarily open to organizations, whether it is a commercial company or a public organization like a university or educational system, to propose projects to make use of the existing space infrastructure. Depending on the specifics, there are grants on the ISS National Lab you can check out to get access to the ISS, and therefore communications and computing capabilities there. There are solicitations like SBIR and STTR from NASA and other government agencies to basically that opens the door to use existing space infrastructure.
All right. Well, just perfect timing here, Alberto. As usual, you did a fabulous job. People are wondering about the slides for this presentation. And we do have the links in our events page at ipnsig.org/events. And I'm going to go ahead and share a screen that has that on it for everybody. There you go. This is where you can find the videos of the past events. And this one we will put up as soon as possible. And Alberto, will you be making available your slides then to us? I just want to confirm that.
Yeah.
Because you had some very detailed slides there, which are phenomenal. And immediately people were commenting and asking about your slides. So, so make sure that you take a look at the other keynotes. Also, if you go into the Zotero library at ipnsig.org and you click on the link for the library, you can just type in a search term of keynotes, and you'll see all of the past IPNSIG keynotes are in our Zotero library as well. If you have any questions, you can write to us at secretariat@ipnsig.org. Alberto, that was just absolutely fantastic, and thank you again. For those of you that are not aware, IPNSIG is a nonprofit group, and we are funded by generous donations. So please scan the barcode here, or you can, if you're in the US, you can text IPNSIG to 53555. Also, we have a donate button over on the ipnsig.org website.
Right. If I may want to double click on that, please, if you found today's presentation useful, put in $5, $10, $20, $1,000, up to you, but put something. There is a lot of work and a lot of effort, that the IPNSIG organization puts into the IPNSIG Academy, the network, and other activities. So funds are always welcome and needed.
Our membership just reached over 1,100 members. We are distributed across the globe, so we always welcome you joining us. If you have any questions about membership, you can just simply send us a message at membership@ipnsig.org. But if you go to isoc.org, ISOC.org, and join the Interplanetary chapter, that's us. We are a group in ISOC as well. And at this point, I just want to thank you again, Alberto. That was a fabulous presentation. And I know that so many people are so interested in building up their competency in space communications. And it's so exciting. And that was just so well done with such great information. I appreciate your time. So
Thanks,
thank
Lauren.
you, everyone.
Good job. Thanks for having me.
Oh, we love it when you present. Thank you, everyone. And you will be redirected to a short survey at the end of this when I close down this webinar. Again, we will have this webinar available as soon as the video is produced. We will pop it up online for all of you. So for that, I'm going to go ahead and close out. And thank you very much, Alberto. We appreciate your presentation. That was great. And thanks for everyone for joining us today. Have a great day.